Let's see. Hi, everybody. Happy Valentine's Day. So, do you receive my email about this afternoon? We're going to have a study session in Snyder 246 from 3:30 to 4:45. Feel free to come and work on your practice exams. So this study session is for all of my math class. So so you might see in my other class. So I will walk around and answer your questions. So yeah, I know today is Valentine's Day. So Valentine's Day was Suki in the afternoon. Okay, so today our plan is to talk about 8.2, and then the exam is next Wednesday, right? Everybody? So the practice exam is due next Tuesday midnight. So if you see the due date on in Canvas, yeah, don't worry about that. Our schedule changed a lot. So but the homework due date, the practice exam due date, even though it's after the due date, it won't hurt your grade. Okay, because right now my setup is unlimited attempt and no deductions on late work. Okay, so but the quiz, if we postpone the quiz, I need to make sure I change the due date for the quiz. So that make a difference. But the homework, the practice exam don't really matter. Okay, yes. Okay, so let's see. Do you have any questions so far? Okay. All right. Let's look at 8.2. So last time we talked about integration by parts. So everybody, what is the integration by parts formula? U
dv
integral u dv equals uv minus integral v du. Louder again. Integral u dv equals uv minus integral v du. Yes. Oh, I have it there. Okay. So yes, that's the chapter 8 concept map, right? So we talk about integration by parts formula. So only two types of integrals. If you have power function and exponential function, we let u to be the power function. Because you differentiate the u, then the power drop down by 1, make the problem easier. Right, everybody? And but if you have power function and log, no choice. You have to let u be the log because we can only differentiate the log. We are not able to integrate the log. So that's why the u, the log, okay? If you don't see the log, then it's the power function. Okay? So that is 8.1. Then 8.2. So let's continue. 8.2. So volume and average values. So, okay. This is application of integral. So definition. We let S be a solid that lies between x equals to A and x equals B. If the cross-section area, so imagine we have a solid here, and then we cut it into slices, and then you get a cross-section area. Looks like a stick, right? Okay, so the cross-section area is A of x, and then the volume of the solid is the sum of the volume of each slice. Do you agree, everybody? The volume of each slice. But for each slice, what is the volume of each slice? Well, that we call volume of a cylinder. Volume of a cylinder is area base times height. Okay, everybody? In this case, what is area base? A of x, the cross-section area, A of x. And what is the height? Do you see the height is this width, change of x? So that's why the volume is sum of volume of each slice is area of the base, A of x, times change of x. So that's why we have this formula, the sum. If you count a lot of slides and you let the number of slides go to infinity, then the sum becomes an integral. And the change of x is now very small, small, small. Then it becomes the differential, dx. Okay? So it's integral A of x dx. A of x is the cross-section area. We focus in the case that's solids of revolution. So we have disk method and washer method. So for the disk method, thank you. Imagine you have a function f and let it be continuous with f is greater or equal to 0 on the interval a to b. If the region R, so this is the region R, is bounded by the graph of f and the x-axis, and then between those two vertical lines A and B, this region is revolved about the x-axis. Can you imagine? You can draw a little rectangle here, and then you imagine what happened to the end points of this rectangle when you rotate. Do you see this point, the bottom point, when you rotate about the x-axis? It remains there. But the top point, when you rotate about the x-axis, we get a circle, right? So the picture is here. We get this. It's a disc. So it's like a circle. Then, so the cross-section area is a circle. And then, what is the area of a circle? Pi r squared. Therefore, we got the volume of this solid is sum of the cross-section area, which is pi r squared, times the width is dx. Is that clear, everybody? So this is the formula. Integral pi r squared dx. And in this case, do you see r is the vertical distance? You know, the distance from the point on the graph to the x-axis? That is the y. So r is the y. It's f of x. So that's why we have the formula v is pi integral from a to b f of x squared dx. Okay? So this is the formula of disk method. Now, what happens if we have two different functions, f and g? Alright, let's see. Do you see if we cut it like this? We get our little rectangle is like here. And then, do you see, look at the end points of the rectangle. The bottom point, when you rotate about the x-axis, we get a small circle. And then the top point, when you rotate about the x-axis, you get a bigger circle. See? So we end up getting an annulus. The annulus, what is the cross-section area? What is the area of the annulus? That is the big circle area minus the small circle area. So that's why the cross-section area is pi and then big R squared minus small r squared. Okay, everybody? So this is the disk method and the washer method. So when you rotate about the x-axis. Okay? So we just focus on those two methods. By the way, so this cross-section area is more general. Maybe we don't rotate about the x-axis. Maybe, let's say, if you have a function like this, And then this part is you make the cross-section area is like a square. Then in this case, square is this height because it's a square. So it's the height and the width is the same. So you get in this case integral your a is y squared dx, something like that, and then you plug in the y. So this is what happens if the cross-section area is a square. Okay, so this formula, the a of x, is more general, and it depends on the shape of your cross-section area. If it's a circle, one circle, then it's pi r squared. Annulus, pi big R squared minus small r squared. If you get a square, then it's the height square, right? Or if it maybe is a triangle or rectangle, and then you get different formula for the cross-section area. Okay, but all the problems we learned in this course is either washer method or disk method. Mm-hmm. Okay, let's look at example 1. Okay, so here I want to show you the concept map. Okay, do you all have the concept map with you? So I have 2 copies. Actually, have 3 copies here. So do you need one? Yeah. You're welcome. Everybody has the concept map. Okay. So how do we solve problems like this? Like find the volume of a solid. Step 1, we're gonna draw the graph plus some integer points, and then figure out the axis of rotation. For our course, we always rotate about x-axis, okay? But in the regular Cal 2 sequence, we will talk about rotate about the x-axis or rotate about the y-axis. If we rotate about the y-axis, instead of dx, your rectangle is going to be horizontal. Then you have dy. Then you get the integral with respect to the y. Okay, everybody? And then step 2, find the region and find the intersection points. So sometimes maybe they give you 2 graphs and you need to find the intersection point to figure out where your x goes from, like where to where. And then you want to draw what happened to the endpoints of the rectangle. Because it's a very skinny rectangle, you just imagine we only have like the 2 endpoints instead of 4 vertices, okay? Because it's very skinny. So you draw what happened to the endpoints when you rotate the rectangle about the x-axis. So we just work with the x-axis. If you get one circle, then that is disk method. So the volume is sum pi r squared dx. If you get 2 circles, one big, one small, then that's the annulus. So the volume is the sum pi big R squared minus small r squared dx. So that is the method. Okay, so let's follow the method and solve examples. Okay, so step 1, draw the picture. So let's draw a nice picture. Okay, we have the x-axis and we have the y-axis. So y equals to 0. You know, y equals to 0 is a horizontal line. Yes? So y equals to 0, this is actually the x-axis. Y equals 7e to the 3x minus 2. Let's plus some points. So let's pick some x values and pick some y values. If we plug in x is 0, we get 7. E to the 3 times 0 is 0 minus 2. What is e to the 0? Yeah. Oh, so what is the answer? Yes, 7 minus 2 is 5. Aha! So we get 5 here. How about when we plug in 1? 7e cubed minus 2? I know it's a big number, right, everybody? So let's say this is 7e cubed minus 2. So we plug in 1 and we get that point. So we connect them. Is that okay, everybody? So, yeah, we just sketched the picture. Now it needs to be very accurate. Okay, we know this is going to be a big number. It's going to be bigger than 5. So then you put a point there and draw it. And then x equal to 0. Bless you. Is the vertical line, right? It's the y-axis. And x equals to 1 is the vertical line. So this is x equals to 1. So this is the region. Okay, so this is the region. This is the region R. Oops. I don't mean to erase that. Okay. I need to get back. Where are we? Okay, here. So this is the region R. And we want to rotate this region about the x-axis. Okay? So this is step 1. You sketch the graph. And then you figure out the region. Figure out the rotation axis. It's always the x-axis for our course. And now step 2. We're gonna cut it. So we want to cut it into slices. Then the rectangle looks like this. The width is dx. Is that okay, everybody? So imagine you have a solid like this, like our cucumber. Do you cut cucumber? This is like our cucumber. And then you cut it into slices. You cut it vertically. You cut it perpendicular to the axis of rotation. So that's why we get this little rectangle. The width is dx. Is that okay, everybody? Now the next step, you draw what happens to the endpoints of the rectangle when we rotate the rectangle about the axis. Endpoints. So imagine we only have 2 endpoints because the rectangle is so skinny, right? So thin. Okay. Look at the bottom points. When you rotate about the x-axis, what happens? It stays here. Right? How about the top point? Makes a circle. Yes. So try to make your graph clean. Don't draw too many lines, too many circles. Then it's hard to see. Okay, make it simple. Just draw one rectangle. And then the 2 endpoints. What happens to the endpoints when you rotate? Okay. So you see, we get 1 circle. So volume is some 1 circle, area of circle, pi r squared, dx. And now, in this case, r is the distance from the point on the circle to the center. That's the center, right? That's the point on the circle. And this is r. Remember, if you have a picture, then the vertical distance is the y. The horizontal distance is the x. So in this picture, tell me, what is the r? Is the r x or y? Y, yes. So r equals y. And y is 7e to the 3x minus 2. And because this is dx, so I got integral with respect to x. Look at this region. Our x goes from where to where? 0 to 1. Yes, this is the integral with respect to x. x goes from 0 to 1. And then continue. Pi r is the y, which is 7 e to the 3x minus 2 squared dx. Is that okay, everybody? Mm-hmm. Yes. So we set up the integral. Now we're going to integrate that. What do you do with the pi? Constant multiple? Put it outside, right? Put it outside. And then, do we have Pareto's rule? Do we have Pareto's rule for integral? The substitution. But in this case, think about it. If we want to use u substitution, that's the u. But then the du, you need to see e to the 3x dx there. But do you see e to the 3x here? No. So we cannot use u substitution. Is that okay, everybody? Because we're missing the e to the 3x. We cannot get a du there. And also, we cannot use integration by parts. Because integration by part, you have some x power and e to the 3x, but no square. Okay? Therefore, this is not in the format of integration by parts. But because it's square, you can actually expand and get a sum or difference. So we move the pi outside, expand. So a minus b squared is what?
A squared.
Yeah. Right. So that's why here we got what? 7 e to the 3x squared minus 2ab plus b squared. Is that okay, everybody? We expand. So we have a sum or difference. All right. So now we distribute a square. What is 7 squared? 49. What is e to the 3x squared? E to the 3x squared is e to the 9x? 6x. Yes. E to the 6x. Good. Minus, what is the coefficient? 2 times 7 times 2. Yes, so 28 e to the 3x plus, what is 2 squared? 4. Oh, yes. See? We simplify them. Can we integrate term by term? Yeah, we have the formula, right? So that is pi. Constant multiple stays here. What is integral of e to the 6x? Yes, e to the 6x. Good. Minus 28 times what?
3x over 3.
Yes. And plus? Yes, good. Evaluate from 0 to 1. Right, everybody? So we plug in 1. Let's plug in 1. So 49 over 6 e to the 6. We plug in x is 1. Minus 28 over 3. We plug in x is 1. So e cubed. Plus 4 times 1 is 4. Right, everybody? So that's what happens when we plug in 1. Minus, we plug in 0. So 49 over 6. What is e to the 0? 1. So is that okay? We don't write it? Because e to the 0 is 1. Minus, yes. And then 4 times 0, 0. Oh, yes. So that's the answer. And then you put this in your calculator. Let's see what you get. Let's see if we get the same answer. Have a calculator? Practice. Type in the calculator. Yes. 3,100. Oh, did you multiply by pi?
Oh, I did not.
Yes. So what do you get?
9,777.799.
799. Okay, great. Yes, I have the same number. Okay. Do you get the same thing, everybody? Nice. So this is example 1. Again, first up, sketch the graph. Okay, and then figure out the region. We always rotate about the x-axis. So we always cut the rectangle vertically. And we get the dx. And so what happens to the endpoints when you rotate about the x-axis? If you get one circle, that's the disk method. If you get 2 circles, that is the washer method. Then you can plug in the formula and no product rule. So when you have a square, expand it. And then so you have a sum or difference, then you can integrate. Any questions about this problem? All good? All right, let's continue. Okay, number 2. Find the volume of the solids obtaining by rotating about the x-axis. The region under the curve y equals x squared minus 2x plus 2 and y equals x plus 6. Just set up the integral. Do not evaluate. Okay, let's see. So we want to sketch. Do you still remember, like here, I give you 2 curves, so you need to find the intersection points. There are 2 ways to find the intersection points. One way is by putting in integer points into the part. You see it. The second way is solve the system of equations. So let's see. Okay, let's see if we can put the numbers and figure out the intersection point. So we have x and y. Here, let's put 0. Okay, so y is the parabola x squared minus 2x plus 2. If we plug in 0, what happens? We get 2, yes. So 0, we get 2. How about when we plug in 1? So 1 squared minus 2 plus 2 is 1. Okay. So 1, 1 here. How about when we plug in 2? 2 squared minus 2 times 2 plus 2 is 2. Oh, okay. How about we plug in 3? So 3 squared minus 2 times 3 plus 2 is 9 minus 6 plus 2, 5. Yes, everybody. So at 3, we got 1, 2, 3, 4, 5. Right here. When you connect the points smoothly, can you see the parabola? Now, can you imagine? Because the parabola is symmetric, so you're gonna know that x is minus 1. Hopefully, we get 5. Yes, everybody? So by plotting the points, we kind of know the shape of the parabola. And we can also see the vertex. Yeah, the vertex is 1, comma 1. The axis of symmetry is x equals 1. So that is the parabola. Now let's see the line. Okay, the line. So we have x and y. Let's plug in 0. If we plug in 0, what happens? We get 6, right? Oh, that is 6. How many points can fix a line? 2 points. We need 1 more point. How about 1? If we plug in 1, what happens? 7. Okay, 1, 7 right here. Okay. That's the line. Yes, everybody? It looks like one of the intersection points is the -1, 5. Let's verify that. So if we plug in -1, what happens? -1 plus x is 5. Yes. Yes. This is it. Yeah, this is actually an intersection point. But we need to find another intersection point, right? Okay, let's try 4. If we plug in 4, what happens? 4 squared minus 2 times 4 plus 2. That is 10. So 4, we got 5, 10. Like, oh, looks like here is 10. Let's check the line as well. Okay, if we plug in 4, what's 4 plus 6? 10. Yes, everybody. Woo, nice. We got both intersection points. So this method is just plotting points. Okay, plotting integer points. Then you can find the intersection points. The second way is to solve the system of equation. The second way, you said x squared minus 2x plus 2 equals to x plus 6. Then you move all the terms to one hand side, you get a quadratic equation. Then you can factor or use the quadratic formula. And hopefully you will get x is -1 or x is 4. And you also find the intersection points. Is that clear, everybody? Now this is the region. We want to rotate about the x-axis. That's the x-axis. So imagine our cucumber. Yeah, that's the cucumber. We rotate about the x-axis, and we want to cut it into slices. Don't cut my hand. Cut the cucumber into slices. We get this. So we get a vertical rectangle. And then the width is dx. Okay, the width is dx. And draw the endpoints of the rectangle. Do you see those 2 endpoints of the rectangle? They're very skinny rectangles. So draw what happened to the endpoints when we rotate about the x-axis. So it looks like the center is here, and you rotate about the center, you get a small circle. And then here, when you rotate, you get a big circle. Is that okay, everybody? We draw the little rectangle, and when you rotate, you get one big circle and one small circle. This is the center. Yes, this is the rotation axis. We rotate about the center.
Wow.
Oh, that's given from the problem. We want to have so we have the region, and then you rotate about the x-axis. The problem asks you to find the volume of the solid when you rotate this region about the x-axis. So which sense? Should you tell me what? Which sense?
I'm trying to figure out how do you know what point to rotate it.
Oh, what point to rotate it?
Yeah.
Oh, like where do I draw the rectangle? Oh, it does not matter. Just draw anyone. But don't draw here, but it's not obvious. Okay, and try not to draw the special point because like if you draw it here, it looks like the big R is 6 and the small R is 2, but no, it's actually changing. Can you imagine this little rectangle is actually changing? Let me show you some picture. Okay, so let me see. Okay, so I have this in my Cal 2. So if you go to the Cal 2 website, and then I have this pictures. Let me see. Okay, this picture. So this is a function. This is like the little rectangle. Can you see the little rectangles go around? So you have a lot of different little rectangles. When it goes around, it generates a solid. Mm-hmm. Yeah. So you can draw the rectangle anywhere you want. Then you look at the top point, the low points. They give you big circle and small circles. Let me see. How about this picture? Oh, okay. So this is when we rotate about the y-axis instead of the x-axis. Then you're gonna cut the cucumber is like this way, and then you cut it into sides. So you're gonna cut it horizontally. So you have dy.
So it's like a disc shape.
Yes. And still annulus. Mm-hmm. Still annulus. Like do you see there's a hole there?
Mm-hmm.
Mm-hmm. Yeah. And let me see. How about number 5? Oh, still y-axis. So you can see y-axis. Then is the integral is with respect to y, and then you see the rectangle is moving around, and then we get a solid. And so in Cal 2, we actually learn more. So our rotation axis is not just the x-axis. It could be any horizontal line or vertical line. Then your big R will change. Okay, so you see this is the center of the rotation, and then this is our little rectangle. Yeah, this is the little rectangle, and then it generates a solid like this. Is that okay, everybody? So we learned the easiest type. We only rotate the x-axis. Okay, no y-axis, no other horizontal line. Mm-hmm. Okay. Yes. So you can pick any, draw your rectangle and but make it generic. Okay, don't make it like at this point. Then it's not clear. Okay. All right. So after you draw the rectangle, you see, big R is from the bigger circle to the center. That's big R. And then small r is from the point on the smaller circle to the center. Now you see big R is the y of the upper curve. Who's the upper curve? The line or the parabola? The line, yeah? The line. What's the line? X squared minus 2x plus 2. Yes, everybody? So that's the big R. Big R is the y of the line. What? Oops. Sorry. The line is x plus x. Yeah. Okay. Sorry. I'm getting old. Y. Small r. Yes, it's the y lower. And then that is the parabola. So x squared minus 2x plus 2. Okay. Yes. You know what? If I split them, my answer will be negative. Then I know I'm making a mistake. We go back and put a minus sign everywhere. Yes. Okay, so our volume is sum cross section area is an annulus. So pi big R squared minus small r squared dx. Okay. Look at the x. So we can move the pi outside. Look at the x. The x is from where to where? This region. X is from where to where?
To
X values. This region. X is from 0. Look at this point. Negative 1, 2, 4. Yes. It's the entire region bounded by those two graphs. So negative 1 to 4. That's why we need to find intersection here. Like, unlike the last problem. Last problem, the problem gives you the x values. But this problem, do you know the x values? Is it given from the problem? No, we have to find the intersection. And then big R, see? Big R is the line x plus x squared minus small r, the parabola, x squared minus 2x plus 2 squared dx. Is that okay, everybody? Yes, because we don't have much time. I want to do more examples. So this example, let's just set it up. We don't evaluate the integral. But you're able to evaluate the integral. This is square, right? You just expand it. If you have 3 terms, how do you expand it? So if you have 3 terms, you just put this, and then you look at one by one, and then next, and then that. So just distribute. Okay, everybody? Yeah. Okay. Any questions about example 2? All good? All right. So let's look at example 3. Okay, so this one, gotta draw the picture. All right, let's draw the picture. And it's set in the first quadrant. So make the first quadrant bigger. Okay. So let's see. Plus some points. If we plug in 0, what happens? If we plug in 0, we get 0. Yes, we get 0. If we plug in 1, what happens? Square root of 2 minus 1 squared, 1. Ooh, what is that? 1. Oh, that 1 is 1. Okay. How about when we plug in 2? It will be square root of 2 times 2, 4, minus 2 squared, 4. So it's 0. Yes, everybody? It's 0. So the picture is like that. Yeah? Excuse me. Okay, now we look at the other one. Okay, what does x cubed look like? Graph of x cubed? Yeah, like that, right? So when we plug in 0, we get 0. When we plug in 1 cube is 1. And when we plug in 2, what's 2 cube? 4? 8, yes. Oh, so it's up there. And it goes like that. Yes, everybody? That is x cubed. And then we want to rotate about the x-axis. See, that's the region. How do you color it? You color it vertically. Then happen to the endpoints. It has 2 endpoints, right? And the bottom endpoint, when you rotate about the x-axis, you get a small circle. And then the top endpoint, when you rotate, do you see you get a big circle? Mm-hmm. So we have big R and small r. Let's continue on Monday. Okay, yes. So this afternoon, study session 3:30 to 4:45 in room 246. Okay. Bye.